One of the nice things about the fact that I've gone and drawn a chart that has strong acids, strong bases, weak acids, and weak bases in it, and that there are only 4 categories for it, means that I can start coming up with symbols that allow me to describe acids and bases so that I'm not writing really big, complicated molecules. I don't have to write something like hexafluorotetraacetic acid, because that's just a lot of letters. That's a big chemical compound when all I'm interested in is the part of it that does acid-base chemistry. So I'm going to be walking into class, and every day I walk into class, I'm going to walk in and I'm going to put 6 symbols up on the board. 6. Those 6 symbols that I put up on the board are the only symbols describing acid and bases. And here are those symbols. There is only one symbol that describes a strong acid, H+. Why? Because when you throw a strong acid like HCl into water and the spectator goes away, all that's left is H+. So why not just write down an H+ and say that's the end of it? There is only one symbol that describes a strong base, OH-. When you see a compound in water and you strip away the spectators and that's what's left, that's a strong base. For the weak cases, there are 2 sets of symbols, and you'll see some parallels here in them. The weak cases include the neutral weak acid and neutral weak base. The neutral weak acid has the form HA. You were not able to throw that chloride away, whatever that anion is. It had to stay behind. So this, HA, is the form of a neutral weak acid. What has this form? Tartaric acid, formic acid, acetic acid. Almost anything that says the word acid is HA. And then there are the weak bases, the neutral weak bases. They're neutral, so when you look in the upper right-hand corner, there's no charge on them. Almost all of these are based upon amines, based upon nitrogen-containing compounds like ammonia, NH3, or some sort of amine like hexafluoroamine. So if you see a neutral that has a nitrogen-containing amine group in it, that is a weak base. So you've got your neutral weak acids, you've got your neutral weak bases. But check this out. If HA, a neutral weak acid, loses a proton, it makes a base. It makes its conjugate base. If my neutral weak base gains a proton, it makes a protonated or charged weak acid. See these nice parallels? This is a conjugate acid-base pair, weak acid, conjugate weak base. Here is a conjugate acid-base pair, neutral weak base, charged conjugate weak acid. We'll learn more about the forms of these and where they come from soon enough. But this is the 6 compounds that I'm going to write, the 6 symbols for compounds I'm going to write down from here on out in all of my acid-base reactions. As soon as I write down the name of a chemical compound, like hexafluorotetraacetic acid, I'm immediately going to scratch it out, and if it's a weak acid, I'm going to write down HA. If I've got something which is a charged weak acid, something like ammonium nitrate, and I take the nitrate part away, and I've got ammonium plus, then I know it's a weak acid. I'm going to scratch everything out. I'm going to write BH+. Once you get this into your brain, and you can use these 6 symbols here to represent your acid-base chemistry, you're going to be fine. But it requires that you be able to label these 4 areas, identify the spectators, and then assign these particular symbols. As I begin the material now, after the series of timeouts to give you all of the background on acid-base chemistry, nomenclature, and symbols, as I finish that up and I get started, be aware that these are the symbols I'm going to use to do my calculations of the pHs in the solutions.